Hey everyone, okay, we are ready to go live. In fact, we are live. So welcome to the final live of 2024. And we're going to be going through a topic that carries on from last week. We went through DNA replication last week, and I had a request to go through Meselson and Stahl's experiment so you can better understand that. So that's what we're going to go through today. I've got a little bit of information on it here that we're going to go through, and then I've got my paper ready. I've got my two different colour pens ready, and yes, I went for festive colours, seeing as it's the last live before Christmas and of this year. If you do follow me on Instagram, I did say if you want to take part, and when I say take part, like make your own notes, you'll need a piece of paper and two different colour pens, but that's going to come in about 5 minutes. Also, I've just realised, I think I've got the wrong thing showing over the top. Let me see if I do that, if it shows. No, it doesn't. So I'm just going to quickly edit it here because what I wanted to show you was you can get 35% off using code HO. So you can get 35% off until midnight tonight, and that is on my flashcards, my A-level notes, and my active recall workbook. But it's only live until midnight tonight, and that is a discount code to say thank you for all of your support this year in 2024, because this is the final live of 2024. So you've got that little discount code down here, ho. Missestrock.co.uk is where you can use it on my A-level flashcards, which I have for AQA, OCR, my notes, which I have for AQA, OCR, and CIE, and then my active recall workbook, which I actually only have for AQA at the moment, but it is coming for OCR in January. Okay, let's begin then. So last week we went through the concept of DNA replication. This week we're going to be going through the evidence for semi-conservative replication, and it does actually say on the spec that you don't have to know this information off by heart. You do need to know this a little bit here, but in terms of the experiment itself, that counts as application. So the key things it says you do need to know is just to have an awareness that Watson and Crick discovered the structure of DNA, and that was in the 1950s. And Rosalind Franklin's research using the X-ray diffraction supported them in getting there. That's like real basic facts you just need to know. There's no more than that on the spec, but that has come up as an exam question before, having to know as Watson and Crick. But what we then need to do is look at Meselson and Stahl's experiment for how they investigated whether DNA replicated conservatively or semi-conservatively. Now, we know as a fact it is semi-conservative replication, which means, as we can see in this image, that you have one entire strand of DNA made from the parental strand, and then you get one newly synthesized strand. So each new DNA molecule that is created is one of the original and one newly synthesized, and that's why it's semi, meaning half, conserved, semi-conservative. But that actually wasn't discovered until the experiment that we're going to go through today, because they hypothesized it could either be semi-conservative, meaning that each new molecule of DNA is one strand new, one strand old, or it could be conservative, where they hypothesized that maybe the two template strands rejoin and the two newly synthesized strands rejoin. And then you get this fully conserved original and you get a newly made one. So that's what the two options were. So as I just said, the semi-conservative replication, this is the accepted hypothesis because of the evidence from the experiment we're going to go through on this paper with the coloured pens. This is where it's hypothesised that each of these newly replicated DNA molecules contain one of the original strands of DNA and one newly synthesised strand. So that there is a 2-mark definition that you sometimes get asked to define what is meant by semi-conservative replication. That's more what we focused on last lesson in the live, which if you missed, it's saved on my YouTube and is it on my Instagram? I think so you can see it on both of those. So the second hypothesis, as I was saying, is this idea of conservative replication. And this is where they hypothesize that maybe the original DNA remains intact. So those two strands that separate to act as templates, the two templates rejoin, and then the two newly synthesized strands joined together as well. And that's what we've got here, these two different colors to represent those two were both newly synthesized, and this redder one is the original. So we're going to go through Meselson and Stahl's experiment, which proved it is semi-conservative replication. So Meselson and Stahl, that is what their experiment is focusing on, proving that DNA replication is semi-conservative. Okay, so a bit of the background about this experiment, and just as an FYI, you do not need to know this off by heart. If you get a question about Meselson and Stahl in the exam, they have to give you this information, but it's helpful if you have an idea of it, because then you'll better understand it, and then when you get to the exam questions, it'd be more like a knowledge question rather than application. So here's the key information about the experiment. They used 2 isotopes of nitrogen in this experiment. And the reason they're using isotopes of nitrogen is DNA contains nitrogen in the nitrogenous bases, which we can see just here. So that could be adenine, thymine, cytosine or guanine. They contain nitrogen. So they use nitrogen isotopes so that when these DNA nucleotides are forming and then the DNA polymer, they'll incorporate the isotopes, and that is going to affect the density of the DNA, which will become relevant for the experiment. Now, as a little reminder, going back to GCSE chemistry, what an isotope is, they wouldn't ask you this in the biology exam, but just as a reminder if you forgot, it's different forms of an element in which the proton and electron number is the same, but a different number of neutrons. So that is what's differing. So they use the 2 isotopes, 14N and 15N. And because 14N has 1 fewer neutron, it is slightly lighter than the 15N isotope, which is slightly heavier. So for short in this experiment, the 14N is referred to as lighter and the 15N is referred to as heavier. So that's the first concept you just need to be aware of, that Meselson and Stahl's experiment, they're going to be using these 2 isotopes of nitrogen, and they're using these isotopes because, first of all, nitrogen is in the nitrogenous bases, 14N is lighter, so you'll end up with a lighter DNA molecule, 15N is heavier, so you're going to end up with a heavier DNA molecule, and that's going to be relevant for what we're going to go on to in terms of what their method was. The next thing is their experiment was all done using bacteria, and the reason for that, I don't know if it's on the next slide. Yeah, we do, I think so. They use bacteria because they're very easy to grow, they replicate rapidly, so you're going to get these results very, very quickly. So there's just some background information to begin with this. What we're then going to move on to is a bit more information. So we've talked about the 2 different isotopes. We've talked about the fact they grew bacteria for this experiment. And what they did was they grew bacteria either in a nutrient medium, which means a solution that contains everything they need to grow, which contains the light isotope of nitrogen or the heavy. And that would then mean that bacteria's DNA would incorporate that particular nitrogen isotope, and it's going to affect its density. So if you were then to remove the DNA from that bacteria, put it in a centrifuge and spin it at high speed to separate out the layers of DNA, the 15N would cause DNA to sink and settle at a lower point in the test tube. And that's because the 15N is more dense. Whereas DNA that contains the 14N isotope is less dense, so it settles higher up in the test tube. And in this way, they were able to grow bacteria with different isotopes and then look at the DNA in that bacteria to see what proportion of each isotope they had by looking at their position in the test tube. So that's the background. What we're then going to go on to is completing this diagram here. I'm going to do it on the paper now so we don't get this reflection so much, but this is going to go through the experiment and their results. So I'm going to shift my iPad over here, and we're now going to go to pen and paper. So what I'm going to do is just a line down here. If you've got a ruler, that's going to be even better, because I'm not going to do a ruler. I want to separate my page into 3 sections. This section I'm going to call generations. So everything that I do in this column is about what generation in terms of reproduction it is. My middle one is going to be visually representing whether the DNA has heavy or light isotopes. So I'm going to say DNA, and this is where the colours come in. I'm going to do the red to represent heavy, which is 15N. I'm going to do the green to represent light, which is the 14N isotope. And then my final column is the DNA. We're going to show the DNA position in a test tube. There we go. Okay, so the first thing that they did was, in generation 0, which means the starting population that they grew of the bacteria, they grew all of those bacteria in 15N. So that's what I'm going to say first of all. Bacteria grown in 15N. And what that will mean is all of the bacteria's DNA is going to incorporate that 15N heavy isotope. So if we then visually draw our DNA to show what that would look like, all the DNA is heavy. I'm going to just show one DNA molecule to start. Instead of doing it as a double helix, because that's going to get more complicated visually, I'm just going to do it as the 2 double strands next to each other. So here we go. There's our 2 strands of DNA. And because they were grown in the 15N, that means all of the DNA, both strands that we have, are heavy. So then if I was to take this DNA out and put it in the centrifuge and spin it at high speed, what we would end up with is one band where the DNA forms. It'll be low down in the test tube, and that is because all of the DNA is made up of one strand of 15N and a second strand of 15N. So 100% of the DNA is made up of 2 chains of 15N. So that is generation 0. What they then did though was, this bacteria that they'd been growing in 15N, before they let it replicate into generation 1, which means our first round of division, they then moved it for generation 1, and the bacteria were then grown in a solution containing the 14N isotope, which is the lighter isotope. So that then means when DNA replication happened, as we said last week, DNA helicase is going to break the hydrogen bonds between these 2 strands, and both strands will separate and act as a template. So that's what I'm showing here. They're separating apart. We have one template strand over here, which was this one. This one's going to move over here, and that's going to be our template strand on this side. Now, when we create our second strand of DNA, that's going to be from all of the free-floating nucleotides, but all of the nucleotides available are now the light isotope 14N. So that means our second strand in the DNA will be the light DNA. So now, if we were to take the DNA out of the bacteria in generation 1 and spin it in the centrifuge, all of the DNA is one light strand, one heavy strand. But that means that the DNA is going to settle higher up in the test tube than this band because it's half heavy, half light. So we still get one band, but it's going to be in the middle of the test tube this time. And that's because 100% of the DNA, that's why we have one band, because 100%, meaning they're all the same, are one strand 15N and one strand 14N. So that's the point that we're at now with our generation 1. They then continued to grow. I've just realised I'm just going to zoom out a bit because I've seen that Instagram can't actually see the whole thing. If you're watching on Instagram, my recommendation is going to be to watch on TikTok or on YouTube, because I actually can't zoom out any further, so you're only going to see the middle bit. But if you are watching on YouTube or if you're watching on TikTok, you can actually see the full screen. So I just say hop over onto one of the other channels. Okay, so generation 2, the bacteria is still grown. Bacteria grown in 14N. So it's still left to grow in the light. Same thing happens, we allow it to replicate, so both of these strands separate to act as templates. But this time we have, that one is a heavy template, that's a heavy template. This one here is a lighter, and that one there is a lighter. But all of the newly synthesized strands will have to be 14N, because that is what they are still being grown in. So that's what our second strand is going to be for all of the DNA molecules. So again, we're going to spin it in the centrifuge, but this time we're going to have 2 bands, because half of the DNA is made up of 2 bands that are just light, and half of the DNA is made up of one heavy, one light strand. So we now need 2 bands, which should be half the width of this one, because it's representing 50%. One is light, so it's going to be higher up at the top. And still we have one in the middle. So that's what you'd now see, 2 bands. We've got 50% for both of them. This one will be 14N, 14N. This one is 14N, 15N. Okay, if we go on to the next round, generation 3 is the last one that I'm going to go on to. You could keep doing this on and on and on, but we're just going to go up to generation 3, which means the 3rd round of division, and they're still grown in 14N. So they're still being grown in this light isotope. Again, all of these separate to act as template strands. So let's just draw in our template strands first. We've got one red, then all of the other templates are green, representing the light. And then the newly synthesized strand on all of them will have to be made up of light isotope DNA. Okay, so now we still have 2 bands, because there's only 2 options, either 2 strands of light or 1 strand light, 1 strand heavy. But now we've got 1, 2, 3, 4, 5, 6, 7, 8. 2 out of 8, which is 25%, is in the middle. So I need to draw a thinner band here to represent 25%. And we have 6 out of 8, which is 75%, at the top. So 75% is 14N, 14N. 25% is 15N, 14N. So this was the experiment that they did, and the way it proves that DNA is semi-conservative is, I'm actually going to swap back to this, is if, I've actually covered it, so maybe I won't, but if DNA replication was conservative, meaning the 2 template strands always went back together, that would mean after the first round of replication, you wouldn't have had what we said, 1 light, 1 heavy together. You would have 1 molecule of DNA that just had 2 light strands and 1 molecule that had 2 heavy strands. And that would mean this is what you would see in the centrifuge results. So you would expect to see 2 bands in generation 1, 1 band at the top where you had the 2 newly synthesized strands of 14N, 14N together, and 1 band at the bottom where it was 15N, 15N bands together. But that isn't what they saw in the test tubes. This is what they saw, and that is how they disproved it couldn't be conservative replication. And then when they carried on doing the experiment and they saw all of these results, this can only be explained through this process of semi-conservative replication, template strands separating, newly synthesized strands aligning opposite. And that is how we got to the conclusion of semi-conservative replication is how DNA replicates. So semi-conservative replication, where we have 1 old strand, 1 new strand in each of the replicated DNA molecules. And that is Meselson and Stahl's experiment. And I did say last week, it's one of my favourite experiments. I think I just like visually drawing it out. One person I think just said they don't understand this last column. I keep thinking I'm on my iPad. I'm like, well, let me zoom in and show you a bit more. But if I just move it over, we'll just literally zoom in like this then. So this last column is if you took the DNA out of the bacteria from each generation and put that DNA into a centrifuge, it settles according to its density. So you get these bands of DNA. This one here settled lower down because in generation 0, all of the DNA was made up of 2 heavy strands. So you get 1 band of DNA lower down because it's made up of 2 15N strands, which is heavier. Generation 1, it was then grown in the lighter isotope. So all of the DNA was made up of 1 heavy strand and 1 light strand, which combined gave a lower density. So that's why the band then settles higher up in the tube because it's less dense. And that's because 1 strand is 15N, 1 strand is 14N. You still only have 1 band though because all the DNA is the same in terms of 1 heavy, 1 light strand. Generation 2 did the same thing again, took the bacteria's DNA out, put it in the centrifuge. Now we have 2 DNA molecules will be made up of the 2 light strands, and that's why we've now got 1 band higher up. 2 DNA molecules are made up of 1 heavy, 1 light, which is why we still have the middle band, but both of them are half the size of this one because it's 50% light, 50% light and heavy. And then same idea here, but now we have 2 out of 8 are the 1 strand 15, 1 strand 14, which is our middle density. 6 out of the 8 DNA molecules are 2 strands of 14N. 6 out of 8 is 75%, so that's why this band is higher, and it's why it's thicker than this one as well. Okay, so hopefully that helps you to understand the Meselson and Stahl experiment. As I said, you aren't expected to know this off by heart. This is an application question, but if you do have an understanding of why they use nitrogen, why they use bacteria, the diagram here of the experiment and these test tubes, then it will help you a lot. The most common questions you get on this are, why do they use nitrogen isotopes? So nitrogen because it's nitrogenous bases. Or you could get, they draw the first test tubes for you, and then they say you need to show what you'd expect to see in generation 2 or generation 3. Or they might show you all 4 test tubes with the bands and ask you to explain those results. And you can use this diagram to explain your result as long as you label it. So you could literally draw this diagram, but you'd need to indicate that that is 15N and that is 14N to show that you're saying 1 strand heavy, 1 strand light, rather than putting it into words. Okay, and that is it for our last live of 2024. And as I said, if you see down here, we've got this discount code that is only running until midnight tonight. So 35% off. You just need to use the code HOHOHO. and that is on my flashcards, my A-level notes, and my active recall workbook. You can get 35% off those to give you a bit of a boost for your revision. And it's a thank you from me for all of your support in 2024, and to say happy Christmas and have a very good year. So, or new year. We'll talk about having a good 2025 in my next YouTube video that I've got coming up. But that is it for today, and that is it for the year. Thank you so much for everyone who's been coming to these lives, whether this is your first one or you've come to all of them. I will be back again on Thursday, the 2nd of January, for the first live of 2025. But that is it for this week. Have an amazing Christmas, everyone, and a great new year. And I'll see you when we get back.